this number here, although I didn't ask for it, you got, should get 3.35, there's a lot more digits here, times 10 to the 6. And then finally, I might as well write this one too. So you get 66.6. And notice I only gave you about 3 significant figures. And like I said, most of the time I give you 3 significant figures. Your book gives you 1 or 2 because he's making believe that it's not quite the same when we work in concentration units as when we work in activities. But I like to see 3 significant figures because then I know where we made a mistake. Okay. So that was that problem. So that reviewed almost everything we did the last time, how to combine equations, how to go from case of B to case of C. Yes?
For number 6, how would you figure out the sign for the IC equation?
Okay, somebody said, and that was the other thing we got into, how to solve problems. And the first step in the problem is already there. Most of the time, that first step is given. In other words, we always usually we give you an equation. Sometimes we'll say the decomposition or the synthesis, but these are not really that type of reaction. So here's the balanced chemical equation. I have to write my equal sign, let's not get into the wrong problem now. And so the first step is the balanced equation, that's right there. The second step, I'm going to write it up here so I can do the ICE table the way your book does it. 2NO2 equals 2NO. 2. Now these all say gas, and so I could either write it as a piece of C or write it in pressure units and talk about case of P, although this one asks about case of C. Okay? So the first thing you want to do is set up the mass action expression. Oh, that's the old name for equilibrium expression. In other words, concentration of NO squared equal 2. And that exercise I gave you on the online homework was essentially, can you write the equilibrium expression and then push your squares and cube buttons and all the rest of it on your calculator. Then what I said you should do, and your book solves things in moles a lot of times and then converts to molarity, and theoretically that's the way you should do it. But since you're always working at a constant volume, the molarity number, I mentioned this to you last time, is the same as the, is proportional to the moles. And lots of times people forget at the end to convert moles to molarity. So I said the safest thing is to convert it to molarity directly and just work in molar concentrations in the ICE table. And when we get to acid-base equilibrium, which we should get to today, you're always working with molar concentrations, okay? So, and I gave you really easy numbers. The NO2, for instance, 0.6 moles over 4 liters equals what? 0.1 0.15 molar. So here's my I, 0.15 molar. And then here's 0.3 moles of oxygen. I should put my square brackets in here so I can see. 0.300 over 4, which is going to be 0.0750 with 4 significant figures. As I say, I don't look at the significant figures too carefully, but you should carry 3 or 4 in your calculations. So that's the initial oxygen. What's this number?
0.
Yeah, it didn't give you anything about the initial concentration, so this starts off at 0. And now the question somebody asked for this one, this side has to decrease, these two sides have to increase. One of the common mistakes I see is somebody put a plus here and a minus here, or whatever. Anytime you start with 0 and subtract, you're going to get a negative number. In chemistry, we don't get negative quantities. In math, you get all sorts of negative numbers, and we are doing math essentially, but in chemistry, you don't get negative concentrations. Anytime you calculate a negative number, it either means, it means you did something wrong. Let's put it like that. And I said the easiest way to do this is to look at the coefficients, and if I call this X, the change in oxygen, this is a 2 to 1 mole ratio, so it's going to be what? And this is a 2 to 1 mole ratio. And so that's the easiest way to set it up, so you get whole numbers. If you would have called this one X, what would this number be? X, this would be?
2x.
A half X. Nothing wrong with that. You get different numbers for X, but X isn't the answer to the problem. X is just a variable you set up to set up mathematical equations so you can solve the mathematical equations. Once you know what X is, you can now calculate whatever the problem asks you for. The problem will either ask you, this is one that says the concentration of NO2 is that number. It says 0.2 over 4. Here's my ICE table that we talked about the last time. It says NO2 is 0.05. This one is 0 plus 2x. This is, I sort of shortened it up a little bit, because when you enter all those zeros in the calculator, it doesn't really matter. Okay, so there's my ICE table. Now, the two types of problems that I talked about, either I want to find the equilibrium constant number, in which case I must have enough information to tell me what X is, or I have the equilibrium constant number that's given, and now I have to set up a mathematical equation to solve for X. Okay? This one is one we wouldn't have to worry about, because if I wanted to solve this for X, I would have the equation, I'm going to turn this off and go that way. So basically, here's the equation I'm looking at. NO is 2x squared. O2, looking over here, 0.075 plus x over because that's the number here, squared. Okay, so C. Now the problem with this, of course, is if you're going to solve this, and I gave you the number for K sub C, this thing right here would be what? A cubic equation in X. And I said your calculator can solve it, but we don't bother doing that in Chem 1B. I was going to say Chem 1A or Chem 2. But we don't solve anything beyond square equations. I guess we could solve something to the fourth power because you take the square root twice But these odd powers like 3/5 and whatever, some x to the third, x to the fifth, we don't bother solving. There'll be one or two problems like that, but they'll be really easy. But something like this would be pretty difficult to solve if we had this number. But without that number, we can, and that's it, the problem says what is k sub c. That must mean we know x. And you look at this, and by the way, some books when they give you this, your book writes everything going down the page like that. Other books are going to sit there and say concentration of NO2 is going to be, and then they'll do the ICE this way because it looks more like an equation. So it would be 0.1500 minus 2x, 0.05, and there's your equals. If you want to do it this way, I don't know what that looks like. It looks like a rotated equal sign. But that's the way your book wants you to think about it. Other books will actually write the tables below the equation where they list each of the molecules. It takes you to write it. What you have to do when you do it that way is you're writing the molecules one more time. So the book was sort of lazy and he just wanted to write the molecules one time. So he puts everything under it. And then you translate it into an equation like this. And you say, oh, look at that. You don't have to show me all these steps. X is 0.05. We just have to say x is 0.05 because you can look at that and say that, right? If not, expand it out and calculate it. You don't want to mess up there. So once you know what x is, you could go right here and say 2x is 0.10. 0.075 plus x is what? 0.125. Now you have all the numbers, you can plug it in here directly, or you know what x is, you can go right up here and say, don't forget the second quantity there, otherwise you won't square everything. And up here you'll say 0.05, doing there. Either way, and now you're ready to get to what the k is. So basically you always set the table up like that, and it becomes a problem of either solving this equation for k because you know k sub c, or you'll do the other problem, which is the one this problem was. You wanted to calculate the value for the k sub c. Okay. What else do we want to do with that?